Okay, so hi everyone, and you're welcome to the next lecture in our machine learning series. And tonight I'm going to look at trees and forests. So trees, I'm referring to decision trees here, and then obviously when we put a number of these together, we refer to them as a forest. Which I'm sure makes sense. Obviously, when you put a lot of trees together, you'd call them a forest. So that's the reason for that. But mostly we're going to look at the decision trees to start off with, and then we'll move on to the random forest. Now, I think in the assignment, I noticed that a lot of you were already trying out some of these decision trees, and that's a good idea. So hopefully, whatever you've learned so far from doing those in the assignment, any of you that have, you'll gain a little bit more from just watching the lecture tonight. So decision trees are a type of classifier network. So once again, we're trying to classify something here. They're very easy to interpret, which means that if causal reasoning is important, then you can be this can be one of the better ways to go about it. So causal reasoning is this idea where if something occurs, in other words, we get a particular result, we'd like to know what caused that result to happen. You can imagine if there's if an autonomous vehicle. Okay, I don't know. It hasn't frozen on my screen over here. Is it frozen for anyone else? No. Okay, so listen, we'll continue on. Hopefully, Shan, it's just a problem on your end, and you can watch the recording later. So, causal reasoning is this idea where we want to know what has caused, what is the reason, or what is the reason for, and what has caused some particular output. And you can imagine that in mission critical systems like autonomous vehicles. If something occurs, we want to know why it has occurred. That's not always that easy when it comes to some of the more complex networks like neural networks, but these decision trees are particularly good when it comes to these mechanisms. So this works because it's very easy to trace our way back up the tree to determine why each decision was made. So it's very logical in that way. In general, trees are upside down with the root at the top and the leaves at the bottom. So you need to think of this as a kind of an upside down tree, a little bit more like a I was going to say a family tree, but actually they're generally the right way up as well. So just think of it as the root node is at the top and we work our way down to the leaves at the bottom. So nodes that are neither the root nor a leaf are called internal nodes, and I'll show you this diagrammatically in a moment. If we get to a leaf node, in other words, where we can go no further, then we've made our classification at that point. So here's how it works. You've got a root node at the top here like this. You've then got a leaf node here as an example of a leaf node because it goes no further from that. But so is this. This is an example, as is this, and this one here. These ones here that aren't either the root node nor a leaf node are called internal nodes. Okay, and we can see two examples of internal nodes there. In most cases, we're going to assume that you just make a binary decision between two things, but it is possible to have ones that make more decisions than that, to have multiple thresholds for when they're making their decisions. So, in order for the order of these can make the decision tree more efficient. So the idea is that if we start making decisions here and we make them there's different orders that we can make our decisions in for making our tree, but depending on the order we make, we might end up having a much bigger tree than is the optimum. Okay, and there's no perfect way of making the optimum tree, so we always try to have these kind of heuristics to try and get us there. So the order of these can make the decision tree more efficient. So at each layer of the tree, we need to make the decision that best splits the data across the child nodes. Now, the child nodes is the idea that this is the parent, and these two would be child nodes of that parent. So when we're making a decision, we need to make the best decision that best separates the data at that particular position. Normally, if we do that, we'll find the most efficient way of making the tree, but it's not guaranteed. So we'll call this maximizing the information gain at each split. And there's a formula for it. So it goes information gain with the two pieces of information that come into it, which is the data at that feature. In other words, the P stands for the parent, the data at the parent node, and the actual data that's available there. Okay. And it's made up of these different parts here. So we can see NJ and NP here. So NP is the total number of samples at the parent node. So what normally happens is that when we're working down through our data, Some samples go one direction, some samples go another direction. So then at that next parent node, we have to split up those samples again and again until we eventually whittle it down to something a little bit more reasonable. So we have NP, which is the number of samples at the parent node, and NJ is the number of samples at a specific child. So we split those up over the different children. And obviously, depending on how many children we have, that's M at a particular node. What we do is we look at the summing up of these. We look at the summing up of these over each of those child nodes. So if M was equal to 3, we'd go 1, 2, 3, and we'd look at this for each one of those. Okay, and we'd sum that up and subtract it from the information that was at this one here. Or say this is actually the impurity, but I'll come back to that in one second. So just to talk our way through this, so IG is the information gain, and it's a function of the parent data set, which is DP, and the feature that we are making a decision on, which is F. Okay, so that's the feature. DJ is the data set or the split for a particular child node. NP is the total number of samples at the parent node, and NJ is the number of samples at a specific child. And then with this function called I, which you see appears here and here, which is a measure of impurity. Okay, so the I there stands for impurity. Now, what exactly that function is, we'll see that there are a number of different options, and that's what we're going to look at. We're going to look at next. So the lower the impurity of the child nodes, the larger the information that's gained. So when we say impurity here, what we really want here is a situation where we get all the samples into one class and none into the other, and that would be perfectly pure, and therefore the impurity in it would be 0. But if we don't get that, we need a measure of how impure it is, and obviously the worst case scenario is that it's evenly split amongst the 3. It's evenly split amongst the number that you have. So if it's binary, it'd be evenly split amongst 2. If it's if there's 3 of them, it'll be evenly split amongst the 3. It's 3 we're going to look at in our example below. So the lower the impurity of the child nodes, the larger the information that's gained. So if we manage to make some decision that that gains us a situation where we get an impurity of 0, then we've got our a large information gain. But if we have a higher impurity than that, then we gain less information by that decision. So if all the data at a node is of one class, then it's pure and it does not need to split any further. Normally we're at a leaf node at that point. And there are a number of competing ways of measuring impurity. The main two are these two here. This one here, it's kind of used for a different system. I'll give a slide on it, but it's not something that's in scikit-learn, so it's not something that's easy for you to play around with. Whereas the other two, you absolutely can use them in scikit-learn, so we'll mention a bit more about them. So the first one is called the Gini impurity. So this can be thought of as a way to minimize the misclassification. So we call it IG just to separate it from the other ones. So this is the impurity, the Gini impurity, and we give it each of the different classes, right? So what we're saying is that a particular node, so we're at a particular node here, and we want to find out the impurity at that node. And what we do is we go through each of the different classes, so from 1 up to the number of classes, and that goes in there. Okay. How familiar are you with this sort of a notation here with this straight line down the middle? Have you come across that before? I'm suspecting some of you have last year but I know many of you haven't done your so I think most of you haven't done the statistics and probability module yet. Yeah, so Stephen has it correct. So it's the probability of I given T. Now, is there anything you could tell me about that number for definite? If you were to give me some definite piece of information about this number, what would it be? And maybe I'm asking a question now that it wouldn't be obvious to you. Yeah, that's exactly what I was looking for. It's between 0 and 1. So we know that that number has to be between 0 and 1. So for any of these, let's say we're looking at class 1, for example, right? So in the first class here, we say, what is the probability of that at this particular node? And we multiply that by the rest of the probability. So let's say, for example, that we have something like it's 70% likely, so it has 0.7 here. Well, what's in this brackets has to be 1 minus 0.7. So what that is going to be is it's going to be 0.7 multiplied by 0.3. Okay. And you can see that this is going to reach its optimum at some point. So just get rid of that from there. So what we do is we go through each of the different classes, we determine its probability and then what the rest of the probability is, and we multiply each of those together. And you can see here that what we're doing here is we're multiplying that by that, and if we multiply that out, we can just end up with what we have here as the following, which is just 1 minus all of these squared. Okay, now you might wonder, well, what happens this multiplied by 1? But the thing is, every one of them is multiplied by 1, and therefore they all add up to 1, and therefore that we end up getting rid of that as well. So it just ends up with 1 minus the sum of all of these. Okay, so if the impurity is 0, then the node is pure. All samples belong to the same class, and you can see that basically if we end up with a 0 here, it means that everything belonged to one particular class, and we can see an example of how that might happen. If the probability of one class was 1.0, then we're automatically going to multiply it by 0 here, and therefore we're going to end up with 0 on the other side. And then for each of the other classes, you're going to end up with a 0 multiplied by a 1 here, and again that's going to end up as 0, and we're going to add them all in. Okay, so that's the unusual case where we have perfect purity. That's not what happens most of the case. So what we're going to do is we're going to look at a binary example here. So I wrote down some numbers here on a sheet of paper, which is why I'm grabbing it here, just so that I know what to work from. So what we're going to assume is that we've got a node. At some node, we've got 203 samples, and those nodes, they're basically separated into 153 of them are of class 1, and 50 of them are of class 2. Okay, so if we go back to our formula here, which maybe I'll just take a copy of onto the next sheet. Let's have a look through this sum. So what are we going to do? So firstly, can we figure out what the probability of class 1 is at this particular point? Well, how we do that is we say that of the 203, 153 of them are of class 1. So that's 153 out of 203. And what we're going to do is we're going to square that. And then we're going to add, because that's what our sum is. And we've only got 2 classes here. So we're going to go for our next class. And our next class, the probability of it at this node, because remember T is the node there, is going to be that over 203. And we're going to square that. Okay. And you can grab your calculator there and check that my maths is right. So we have to have 1 minus this. So we'll have 1 minus 153 divided by 203. I got, I think it was 0.754. And that wasn't squared yet. And then, and we want to be careful here. It's minus all of that together. So what I'm actually going to do is I'm going to say that that's a minus, so that we see it in there. Okay. And then 50 over 203, I got, what did I get for that? 0.246. 246. Maybe use a smaller thing. Squared, and when I squared them out, I got 1 minus 0.5625, and minus this ended up being quite a small number. It was 0.0606. Is that correct? Looks wrong. 246 squared. No, it's correct. Okay. And when we subtract all that out, I end up getting 0.3768. Okay. Now, if you go through this, you can basically find that if we were to split this 203 as evenly as possible, you're going to end up with a bigger number than that. But if, let's say, we were to split it like this, we were to say out of the 203, class 1 has all 203 of them for class 1 and 0 for class 2. Okay. How would this work? Well, we'd have 1 minus, the probability here is 203 over 203, square that, minus the probability of 0 over 203 squared. So that's going to be 1 minus 1 squared minus 0. Anyone want to help me out with my maths there? How does what's the answer to that? I'll give you the easy one. Yeah, it's just going to be 0. Okay, so it's going to be 1 minus 1 minus 0, which is going to be 0. Okay, so what does that tell us? Well, that tells us that it's 0 impurity, or it's absolutely pure, and it's absolutely pure because it's all of the one class. Okay, so therefore we could be at a leaf node and we wouldn't need to split it any further. Okay, so you can see how this system works. This would be for a binary classification problem, but you can see how for something with 3 classes, all we'd have to do is find out, well, how many, and you'll see an example of this in a few minutes, how many of each class there were at that, and therefore we could we just have a third of these guys, 1, 2, and another one here, 3, and we'd work through it all. Okay. Now, entropy, so basically just to remind you, there are a few different impurity methods. We said Gini, entropy, and classification error. So that was Gini. This next one is entropy. And entropy is a term that's used fairly often in physics, particularly to do with energy and what happens energy, and it tends towards entropy, where it's more complex. In this particular case, what we generally talk about here is entropy to do with data or information, and generally it's to do with how difficult it is to put one system in another system's form. So, for example, if you were dealing with binary systems, as in binary numbers, you might say, well, okay, how difficult is it to put it in this particular coding form than in another particular coding form? So it's the amount of bits that it would take is the answer to that. That's not too important for you from your point of view, but you can see that's basically why the log 2 is used here, because we're trying to find out how many binary bits it would take in order to actually represent something. And the more that it takes, the more complex the thing is. So all that's really different here is that you'll notice that we don't have any one anymore. Okay, so we're not subtracting from 1. We have still got a minus here. Okay, so we have got a minus here, and it's a minus by all of this, which means that we're going to sum all of these together and then multiply them by minus 1. Now the reason for that is that this log number, so we're getting the log of a probability, and that's maybe something that's worth us just pausing on and thinking about. So I asked Stephen, or Stephen answered me earlier about what was special about this probability, or tell me something about it. And he said, well, it's always between 0 and 1. So my next question to you is, if I get the log of a number that's always between 0 and 1, what can you tell me about the answer to this? Yeah, and Maria has answered it there very quickly. It's always going to be a negative number. So therefore, no matter what we do here, this number here is always going to be between 0 and 1, as is this. This overall number here is always going to be negative, which means this overall number here is always going to be negative. We're going to add 3 negative numbers together. What do we really want to do at the end? Well, we just want to multiply them by minus 1, so we bring them back to being a positive number. And there's no real other reason for that, except to say that we'd prefer it to be a positive number than a negative number. But actually, it's not really adding much information to do that. But we do that all the time, and that's one that's important to kind of keep in mind, because it comes up again a lot in neural networks and things like that, in cost functions. Right. So it's very, very similar, really. And so if the entropy is 0, the node is pure. All samples belong to the same class, if that's the case. And in practice, Gini and entropy will give different impurity values, and we'll just work through our example again just to show that. But they'll optimize in a similar manner. So no matter which one of these you use, you're going to end up likely with the same tree or something very, very close. There might be small differences between them. So let's take an example, and what I'll do once again is I'll just take a screenshot of that and we'll bring it over. Okay, so I think my example from the last time was I had 203 and I was splitting that 153 and by 50 for class 1 and class 2. So if we look at this, we've got a minus outside. We're going to take the probability of I given t, which is going to be 153 again over 203. And we're going to multiply that by the log to the base 2 of, again, the same number, 153 divided by 203. From that, then, we're going to subtract again the next one, which is 50 over 203 times the log to the base 2 of 50 over 203. Maybe try and write that again. Okay, nothing too difficult here. Obviously, the 153 over 203, we worked that out earlier. So what I'm going to do is, I'll just write it here. It's going to be minus 0.754 times log to the base 2 of 0.754. And we're going to go minus again. Sorry. I've done it correctly above, but I didn't do it correctly here because I didn't need to take that off. And we're going to subtract from that because the minus has to multiply all the way in. 50 divided by 203, we said was 0.246 times log to the base 2 of 0.246. Now my next question to you is going to be, so we put that around there. Thank you. Thanks, Ratko. Okay, so there's a plus in there because, of course, and there should be a plus there because it's all going to get multiplied by minus. So I'm managing to confuse myself. Right. The next question then is, how do we get the log to the base 2 of 0.754? So check your calculator there and see if you've got a log to the base 2. And I'm betting you don't, because my one certainly doesn't. So there's a trick, there's a way around this. So if anybody knows the way around it, let me know. Otherwise, I'm going to tell you. Yeah, and Stephen has actually told us there. So you get the log of 0.754 divided by the log of 2. Now, here's a question for you, Stephen. So, and this is somewhat of a trick question. Is that log to the base 10 or is it log to the base e? Is it the natural log? Anyone else can throw in their tuppence worth here. Do we get log to the base 10 of 0.754 and then log to the base 10 of 2? Or do we get log to the base e off those two numbers? Yeah, exactly. So either of them, and Ratko's answered that as well. So either of them will do, it doesn't really matter. And you've got both of those on your calculator, but I think most calculators don't have log to the base 2. What we're going to do is we're going to get log, I'm going to use log to the base 10 of 0.754 and log to the base 10 of 2. Multiply that by 0.754. Plus 0.246, and that's going to be by log. And you can be working out some of these numbers for me. I have them worked out, but no harm you trying them yourselves. So that's going to be 0.754 over log to the base 10 of 2. Okay, so minus. I think that's what Ratko was trying to tell me there, but don't not forget the minus. Okay, so log to the base 10 of 0.754. At least I thought I had this worked out. I think I'm getting minus 0.1228. You can let me know if you got something other than that. So minus 0.1228. I think I didn't work out log to the base 2. I think I just used it. So log to the base 2 is 0.301. 0.301. And we'll do the same there, 0.301. I've put the wrong number up here. Okay. So then we'll get log to the base 10 of 0.246, and that came out as minus 609. Minus 0.609. .754 and minus outside of it all. Okay, so this number here down there, I got minus 0.407, and we're going to multiply that by 0.754, so 0.754, and we're going to add to that 0.246 by, what should I get for this, minus 2.023. Minus 2.023. Okay, and I think I stopped at that point. I didn't actually work it out. So 0.754 multiplied by 0.407. So I'm seeing minus 0.306, and add to that, I'm seeing 0.246 multiplied by 2.023, so I'm seeing minus 0.4976. okay, and a minus on the outside, so we'll add to that 0.306, and we're getting overall and getting minus 0.8036. okay, so you can check my arithmetic there. There's a good chance that I've made a mistake somewhere there along the way, but but you can see the general idea of what we've come up with there. Okay, and you can see that the number that we've ended up with there, this number here, that number there, is different from what we worked out over here. Okay, so it comes out as a different number, but you will find that nonetheless it will sorry, that should be a plus, of course. It should be a plus overall when we put in the other minus. You will find that nonetheless it will optimize to the same point. One last thing that we should do here is just take a look at the situation that will occur, and I won't need too much space for this, so we'll do it down here. What happens in the case where I have absolute purity? So I have 203 for class 1 and 0 for class 2. What happens in that case? So let's have a look. We've got a minus on the outside. We get 203 divided by 203 times log to the base 2 of 203 divided by 203. And then I'm going to add to that 0 over 203 by log to the base 2 of 0 over 203. Okay. What this turns out to be, another one there, is 1 times log to the base 2 of 1 plus 0 times log to the base 2 of 0. Okay. So does anyone know what log to the base 2 of 1 is? You don't even need to go the long way around it. Yeah, it's just 0. So this is going to end up being basically 1 by 0 plus 0 by Well, the log, does anyone know what the log of 0 is? Yeah, it's undefined. But this is multiplied by 0, so we're pretty much okay. So basically, we're just going to end up with 0, minus 0, plus 0, doesn't really matter. And therefore, you can see the situation that we've ended up there. We've still managed to get 0 impurity in that situation. Okay. Right, we'll move on, and unless anyone else has any question. Yeah. Okay. So classification error, I mentioned that there was a third one here, and classification error is useful for, it's just basically 1 minus the maximum of them. It's useful if you're pruning the decision trees, but not recommended for growing them, which is mainly what we're going to look at today. So pruning them is where you kind of go about and you say, well, this leaf isn't, or this leaf node is not really adding much to the overall thing. I'm going to get rid of it. And you might do that on the basis that if your tree is going out of your way in order to deal with just a single data point, it doesn't necessarily make it a good thing to do, because that's generally a case of overfitting. So generally pruning is used as a mechanism to stop overfitting. This one is less sensitive to class probabilities of the nodes. Pruning and classification error are not supported by scikit-learn, so that's why I'm leaving them out in this particular thing, but I don't want to just go by without mentioning them all the same. So let's look at how we're going to build a decision tree. So decision trees split the feature space into rectangles, and the deeper the tree, the more complex the decision boundaries. Just as we saw with other methods, this extra complexity may not be a good thing, as it could just overfit to the training set. And generally speaking, you'll nearly always find that it'll find a way, if you just allow it to go as deep and deep and deep as it can, of splitting up the space in some way. So I've taken the exact same data set that I've been using kind of all the way through, which is a very, very limited data set, only a small set of numbers in it. And what we're going to do is we're going to have a look at how the decision tree would break that up. So just to remind you here, I'm using the pixel depth, I'm using the pixel brightness on the bottom here, and I'm using the position in the frame. And remember, it was where we were trying to figure out just from those two pieces of information whether something was a road pixel or not, right? We're not too concerned here. I've set up 3 different things for maybe 3 different labels. I can't remember what my 3 different labels were. I think one was road and the other was maybe a road sign, and then the other was we just had other. And as you can see, there's a bit of crossover between the green and the blue there that's going to make it a little bit difficult here. But the first decision that it's made is to put a decision boundary just here. And basically what it's saying is we're going with position here, and if the position is smaller than or equal to 0.45, which is there, right, then what we're going to do is we're going to split the data one way or the other in this particular case. You can see that it's worked out an entropy score there of 0.065, so this is far from pure. And what it's saying is that we've got 12 of one class, 11 of another class, and 13 of another class. So these are not quite balanced, but they're not far off. And what we're saying is that if it's below 0.45, we're going to have this one down here. And you can see what's happened here. It said that of my class number 1, all 12 of them have gone down here. Of my class number 2, which is 11 points in it, this is the blue class, by the way, so maybe we'll just color that blue here. Okay, so this is the blue, no, smaller than that. So that's the blue class, and what we'll do the red class there and the green class there. Okay, and you can see that the 11 of those has been split into two there, and 9 of them have gone down here. And basically your 2 are those 2 there have fallen below the line, and the other 9 are these ones here. Okay. So once we've got to that point, then what we have is we've ended up with 14 samples. 14 samples which are effectively below this line here. And they're split up into the 12 and the 2. And we also down here, we have 22 samples above the line, and they're split up into the 9 blue samples and the 13 of the green samples. And at this point, we're then going to try and make a decision as to how we're best going to split up the data from here. What's our next decision that we're going to make? So this is a tree of depth 1, by the way. So the depth starts there. Obviously, you can't have a tree of depth 0 where you just have that, because then you haven't made any decision on the data set at all. Okay. We don't have any leaf nodes here either yet, because we don't have any position where we've got our impurity down to 0 and where we can definitely say that once we're at that, we're at one class or another. All right, let's see what happens next. So what happens next is we can split up both of these. So this one here, what we've basically said is we're going to say if the brightness is smaller than or equal to 0.85, what that's going to allow us to do is to take all 12 of these, put them down there, and none of the other classes. Okay. Meanwhile, the other 2 will go in this direction here. So let's have a look at that. So this is below 0.85. Okay, which is that line there that it's drawn. And basically what it's allowed it to do is those 2 that were a bit confused and were below the line here and in with those, they're now in a section that goes in with all the rest of the blues. Okay, so we don't mix them up now anymore. And so this one here is basically drawing that line there. Let's have a look at this line here. This is saying brightness smaller than or equal to 109. But this doesn't make a perfect split. On the one side, yes, of these 9, none of them go down there, and all of them go here. But unfortunately, that 13 has not got perfectly split. It's gone 9 one way and 4 the other way. So let's have a look at where that line would be. It'd be at 109, which would be somewhere around. Well, actually, sorry, has it drawn in the line? It has drawn in the line, sorry. So it's drawn that line there. And you can see that what's happened in this particular case is that we've got all the blues out in one section, but the greens, 4 of them have gone over there. And that's that 4, whereas 9 of them are over here in this other one. And admittedly, the 9 are over there on their own, so that's pretty good. If you land down to this leaf node here, where your entropy is 0, you can see, well, we've made a decision. Same here. If we land down to this, we've made a decision. We know exactly where we are. If we land down to here, we know exactly where we are, but here we don't. We're still a bit unsure. So if we're in this section here, we're not entirely certain where which one that we're dealing with. Let's see what's our next move. Now it looks like nothing has changed here, but in effect that's because we haven't got ourselves fully figured out here. So what we've set a number here of 100 and, well, that's that 168. The 9 and the 4, which is that one, 109. Yeah, so 168. So where is that? That's about here somewhere. So we've a line somewhere around about there, and what it's obviously, sorry, it's probably there. So it wants to have all of the greens on that side of it, is what it's saying. So if it's smaller than or equal to 168, it's basically saying that that our greens are all going to go in one direction. And if it's bigger than 168, then they're all going in the other direction. So we've got four samples there that have gone in that, 9 in the other. Okay. So I think that's what it's doing there. So let's have a look at what it's done. So there's our 168 line. Finally, what's happened here, once we've got down to that, is we've gone back to doing our position, and we've said smaller than or equal to 0.65, which is that line there. So we have that line there and that line there together before we actually managed to split them off. Okay. What's happened here now? All the green has gone into this section, so that's pretty good. But we still have these 2 blues out here on their own, which we're going to have to figure out. And that's what's basically held up here. We can see that we've got 2 of the blues and 4 of the, I don't know whether you can see them, but it's 2 of the blues and 4 of the greens in that area there. So that's what the final chunk of the tree is going to try and do. Well, it's actually going to have to do it in 2 steps, unfortunately. So you can see here that what it's done is it's split it up into 3 of them have gone one way, so it's dealt with 3 of them, those 3 there, and then the other 2 and the 1. So that's the 1 and this is the 2 is our problem. So we're going to have to go 1 step further, and we're going to have to split those 2 and the 1 into 1 going that way and 2 going this way. Okay, so you can see the line that is created here. Okay, now that can get a little bit complex as it goes, and I'd advise you to go back through the notes, zoom in on them there, and see how it's made each decision as it's gone down and what it's done. The difficulty here is that this is a typical example of where you could get something like overfitting. If that happens to be a sample maybe that's not really very representative of the rest of the data, then we could have a problem whereby we've made a special section in here, but actually it turns out that when new data of that type comes along, it mightn't necessarily be there. So in other words, you might have a new blue one come along. It might be just there, and you can see the problem that's going to happen there. It's going to be classified as being class 2 instead of the other one. So you can see the classic sort of overfitting. So one of the ways to stop overfitting is to say, I'm not going to allow you to go beyond a certain point. So I'm going to say I'm going to restrict you in the number of layers to your tree. And by doing that, so by restricting the depth of the tree, that's one of the ways that we stop overfitting and make it a little bit simpler. So you can see that these trees, the way they divide up the space is all in terms of straight lines and so on. It's very different from what you would have seen with things like logistic. Well, it's not, logistic regression did something similar, but if you wanted to do it with a more complex model like a curved model, that's not easy to do, or it's not possible to do with a tree. Instead, though, the tree, as you can see here, can deal immediately with the situation whereby we've got 3 classes, whereas with the other ones you were looking at basically using several binary classifications and then trying to use them together in order to figure out what you were doing. So they're an interesting idea. Let's have a look at how well we did after, because bear in mind, while if we restricted the tree here, you might think, well, we don't solve all the problems, but we do still have a model if we have some new set of data that comes along and we say, well, where is it going to be? So let's see how well do we do, because I always hold out a validation set that I'm going to test on it. Admittedly, it's only a small set of numbers, but nonetheless. So you can see that training at depth 1, we only had an accuracy of 0.69, and my validation accuracy was 0.56. If we go to depth 2, it improves to 0.888, and my validation score is actually even slightly higher, and that can sometimes happen. Doesn't improve as we go to depth 3 in either case, but at depth 4, my training does improve, and my validation score in that particular case comes out at 1. Then my training score at depth 5 goes to 0.97, and this goes to 0.93, and here training score goes to 1.0, and my validation score goes to 0.93. So you can see here that for my particular set of data, it might have been better sticking at this, where it seemed to be a bit more generalized of a model. But, you know, it's a little bit iffy there because I'm only using 32 points to train and I have 16 points left out for validation. So really, if I had more data, we could build a better model here, and that's the kind of the mantra of most things in data science. Okay. How are we doing for time? We're okay. Okay, so we're going to go through some advantages and disadvantages of decision trees, and this is all you can find these written in the scikit-learn website. I've taken it directly from there. So the first thing is that they're simple to understand and to interpret. So unlike things like neural networks and so on, where it's very difficult to determine why they've given the result they have, for decision trees it's very easy to work your way back and say exactly why they took that, because if you take any decision that was made, you can basically work your way down the tree down to that decision and see why it made the decision at each point along the way. So that can be useful, and it's causal reasoning. So that's because trees can be visualized. It requires little data preparation. So in actual fact, unlike, you know, the assignment that you're doing at the minute, if you're doing you know, some of the other classification systems on it, and you're probably doing some scaling of your features because some features are much bigger than others and you want to kind of have them all in roughly the same range, you don't really need to do a lot of that data preparation here, because the decision tree will make a decision as to where it's going to cut it, and therefore it doesn't matter as much. So other techniques often require data normalization, or they need dummy variables needed to be created and blank values to be removed. That's not as big of an issue when it comes to decision trees, and the reason for that is you only make decisions on a subset of features at any given point. So if you don't have a value there, you just don't make the decision on that feature at that particular point. The cost of using the tree, i.e. predicting data, is logarithmic in the number of data points used to train the tree. Now this is an interesting one, that if I have more data points, I end up having more decisions to make because I'm trying to split it up. So it turns out then that the number of data points that I have has some determination on when I later on come up with a new sample. I have to work my way down through the tree, and if I had more samples originally, it'll take me longer to make my new predictions. That's different from most other models. The data has an effect on it, but it's logarithmic in that basically what happens is that as my data gets bigger, it doesn't get bigger linearly, it gets bigger logarithmically, which means that it's actually not as bad over time. The bigger we get, it doesn't add as much each time. And that logarithm is to do with the fact that we're dividing by 2 in each case. It's able to handle both numerical and categorical data. So again, in the case of your assignment, where you know particularly your classes, you're having to turn them into probably different values. But as well as that, if you have some data that just gives a class value or has some sort of word associated with it. So let's say, for example, it's not in that data set that you have, but what would be a good example of this? I was about to say gears, but again, you could turn those just into a number. Well, actually, no, gears is fine, because rather than them being a number, it's not like third gear is 3 over 2 times second gear or something like that. So they're not really numerical values. They're a class. They're what gear that you're in. If that was in your data set and you could determine what gear you were in, that wouldn't be a problem. You wouldn't have to turn that into a numerical value in this particular case, because you literally just make a decision based on it. So you would make a decision based on what class that was as to how you're going to separate down through it. So it can handle both numerical and categorical data. Other techniques are usually specialized in analyzing data sets that have only one type of variable. So, you know, usually just a numerical variable. They're able to handle multi-output problems, whereas we saw with logistic regression, what we were going to have to do is if we had 3 of them, we were going to have to make several binary classifiers, and we're going to have to do that one versus all, which is it's fine, but it'd be nicer if we were able to include it all in one model. It uses a white box model, and by white box here we mean the opposite of a black box. So what we're basically saying is that it's transparent. We can see exactly what's happening. Some other systems are black box in that you haven't got a clue what's going on inside them, or they might be kind of considered grey box, which is you're kind of semi-transparent. You have some idea what's going on, but and you can work your way maybe back through it, but maybe not as easy to see as something like a decision tree, which is very, very transparent in what it's doing. So if a given situation is observable in a model, the explanation for the condition is easily explained by Boolean logic. By contrast, in a black box model, for example in an artificial neural network, results may be more difficult to interpret. It's possible to validate a model using statistical tests, and that makes it possible to account for the reliability of the model. So you're able to do lots of statistical tests on this and determine, particularly with your validation sets and so on, you're able to determine how often it gets it right and how often it gets it wrong. And even if you prune the trees, you can still say, well, with some definiteness, it's this value, and I'm 97% certain. So those things are useful when it comes to these things, because we want to know, what its reliability is as a model. It performs well even if its assumptions are somewhat violated by the true model from which the data was generated. This is a kind of a difficult concept to understand, but if the original underlying model might look nothing like this here, like the decision tree, so it might build it up in such a way that looks nothing like the original model, but nonetheless still seems to work well, because most models would not look like that rectangular sort of fashion. It'd probably be something more curved, but that's fine. It still works quite well despite that. There are lots of disadvantages, though, to the decision trees. So decision tree learners can create overly complex trees that do not generalize well. And so the generalization problem is a difficulty. So what it does is it tries to get all of the data perfect, and because it's doing that, it overfits to that data. So mechanisms such as pruning, which is, as I say, not currently supported by scikit-learn, or setting the minimum number of samples required at a leaf node, or setting the maximum depth of the tree are necessary to avoid this problem. So I mentioned the depth of the tree, and you could see how that was going to have an effect. But you could also do something like this. That only has one sample at that leaf node. That's already suggesting that you've gone out of your way just to deal with that one particular node. So you could set and say, well, the minimum is going to be 3, which would allow for that one. But basically, this one would have to stop at this point and say, well, it's a 2-for-1 odds as to which one you're going to get. And you can either choose that as choose it randomly between those options, or you could decide, well, I'm going to say the probability is that it's the one with the 2 rather than the 1. Okay, but that will generally that might work better for for new samples coming in and not overfitting. Decision trees can be unstable because small variations in the data might result in a completely different tree being generated, and this problem is mitigated by using decision trees with an ensemble, which we'll come back to in a moment. So let's just go back here. You can see that line that's come in there, had that green dot just been something slightly to the side of that, we'd have something very different. As well as that red dot there, had that just been slightly higher, you can see the trouble that we're going to have there, and the different complexity of the model that we're going to have to create for it. So, and remember that this is just a bit of data from the data set. It's not something about the model. And it could easily be that just because you have that one there, it could easily be that the red set could have one that's above that. And therefore, the line was set simply because of the data that we happen to pick. And I split this data up into, was it 32 and 16. Had I happened to take a different 32 out of my overall set of 48, you can see how I might have ended up with a different model from that. So we have ways of dealing with that. It's called a model ensemble, and we will, as I say, we'll come back to it in a moment. So, by the way, actually, one note I wanted to make about slides. When I'm delivering a lecture, and this goes for all lecturers, our slides double up as being your notes. Okay. So I don't want you to look at this and say, well, this is the appropriate way to present. This is not the appropriate way to present if you're ever presenting to an audience. There's way too much text on this. It's simply that you're looking at a computer here, and I'm working through this very, very slowly. So when it comes to if you're presenting for any projects, but also if you're presenting at work, you need to keep very little information on the slides. So try and keep it to maybe 5 to 7 objects on the slide, so 5 to 7 words in a sentence, maybe only 3 or 4 sentences on a slide. Try and keep it as small as possible. And so I just mentioned that at this particular slide here because oftentimes people assume that when the lecturer tells you you shouldn't present in that way, and then you say, well, you do it all the time. It's because we have a different we have different needs that we're trying to meet, and in this particular case, what we're trying to do is we're trying to teach and present, but we're also trying to give you a set of notes, and that's why I end up with a lot of text on one slide. But it's not a good idea for in general presenting to put this much on one slide. But going further back into the disadvantages of decision trees, the problem of learning an optimal decision tree is known to be an NP complete problem under several aspects of optimality and even for simple concepts. Now, I don't want to go into detail on this. You can see I've written a few notes about what NP complete means. Firstly, NP complete stands for non-deterministic polynomial time. That's not easy to understand, but basically what it's saying is that we know that it should happen in polynomial time, which means there's some polynomial that we can multiply, or we can, sorry, I don't want to say multiply, but there's some polynomial function that we can take the number of samples that we have, put it through that polynomial function, and that will tell us the amount of time that it takes to run this algorithm. The problem is we don't necessarily know what that polynomial is. Okay. And so NP problems are problems where we don't know, is there a fast solution to this or not. So if you take things like the Fourier transform, which I'm sure many of you did in the past, Fourier transform takes huge amounts of time, but somebody went and found the fast Fourier transform, which is a very, very quick way of doing that. There's a whole set of problems that we have, which are called NP, and basically we don't know if there's a fast way of doing them or not. And we may never find a fast way of doing them, or we might. We're just not sure yet. MP complete problems are a subset of that, where they basically, once again, we don't know if we can solve them quickly or not. But if we solve any one of these quickly by a fast mechanism, we then have a mechanism to solve them all. Okay, so they fall into a particular set for that. The main thing you need to take from this is that decision trees, we might not have the most efficient, we definitely don't have the most efficient mechanism of solving them, but we don't know if there's a more efficient mechanism or not. So we don't know if there's some really quick way for solving them or not, is the problem. And that then means that as they grow bigger in terms of data, then the problem to solve becomes bigger. Okay. For these problems, what we can at least do, though, is for MP problems, is that we can check if they're correct or not, and we can do that in a very short amount of time. So Sudoku is a perfect example if you've ever done it. We don't have a mechanism to solve that. Some Sudoku problems can be solved quite quickly, but if you go up to, instead of 3 by 3 boxes, if you go up to 9 by 9 or 100 by 100 boxes there, computers, we don't know if there's fast ways to solve them or whether they just literally grow and grow and grow. But we can, if they solve it, we can check it quite quickly to see if it's correct. And it's the same with this problem as well. Some of the other disadvantages, there are concepts that are hard to learn because decision trees do not express them very easily. So things like the XOR gate, parity or multiplexer problems, those are actually quite difficult for decision trees to do. XOR and things like that can be solved with neural networks, and it's one of the kind of toy problems that people do. Decision tree learners create biased trees if some classes dominate. So you can see how in the previous case I had slightly more of one class than another. If you have more of one class than another, then you end up with a tree that's biased towards that because there's more data points for it to work with. So it's therefore recommended to balance the data set prior to fitting with the decision tree, and that generally goes for nearly all of the classification mechanisms. You want to balance the data set by some mechanism. The simplest, obviously, is to remove enough of the samples off the bigger class until you end up with an equal amount of all the other classes. And you should really do that. Again, in your assignment, you should be doing that as well. Okay. This brings us on to the final section of the lecture tonight, which is called Random Forests, which is where we take lots of decision trees somewhat randomly, and we look at the results of them together and see what the result is that we get. So this is basically an ensemble of decision trees. So this word ensemble pops up all over the place as well. It's where we use multiple models together and we have some form of voting system amongst them as to the result that we get. So an ensemble uses the idea of the wisdom of the crowd but applies it to models. If you're not familiar with the wisdom of the crowd, the idea here is that lots of people who know some little bit of information but don't know it all, if we take all of their information together, we're likely to end up with some central value which will probably be correct. And the typical example of this is where people try and guess how many like pennies are in a jar, or what the weight of some animal is. You'll see it at a lot of these fairs. You have to try and guess the weight of something or how many items are in it. And generally speaking, what you'll find is that while some people may be way out, others won't be way out. And what happens is that if you were to take an average of enough people, you'd find that they'd guess it very, very close to the actual answer. So that's the idea of the wisdom of the crowd. But this one, the idea of random forest is that what it does is it applies that idea to these decision tree models. So when we create an individual model, it may not be very good, but combining many weak models can give a much stronger and robust result that generalizes better. So the random forest algorithm works as follows. You draw a random bootstrap sample of size n, and this is where you randomly choose n samples from the training set with replacement, i.e. there can be duplicates. So what we mean by this is that if we take, and I'll just draw a very small data set here. Let's say that these are numbered in order for the sake of argument. 4, 5, 6, 7, 8, 9, 10. And I'm asked to draw 5 numbers from this. Okay, so let's say I draw the number 4 first of all. and then I draw the number 6. What I can do is I can draw the number 4 again, because there's nothing to stop me. I'm just putting my hand in. So this is what we mean by with replacement. Okay, and then maybe I draw 7, and maybe I draw the number 4 again for some reason. Okay, so that's now a set of n samples where n is equal to 5. So and that's them there, and you can see with replacement, which means that I can draw the same number multiple times. So we draw that, and we grow a decision tree from that. At each node, what we do is we randomly select D features. So we don't necessarily pick the best feature. What we do is we randomly select some set of the features, assuming we have lots of them. Again, this time without replacement. So we're not allowed to select the feature twice. So we're not allowed any duplicates. We split the node using the feature that provides the best split according to the objective function. So for instance, by maximizing the information gain using one of the ones that we used earlier. Now the point here is that if I have 20 features and I only select 10 of them, I'm not necessarily going to split at the best feature. I'm going to split at the best within that 10. And so it might be that we just didn't pick the one that has the best split. But it's some later tree we will get the best split, and so this gives us lots of different trees from this mechanism of doing it. We repeat this step 1 to 2, and just be careful that k is a constant. It doesn't mean 1000. So 1 to 2 k times. Okay, so whatever we pick our value k to be. And then what we do is we aggregate the prediction by each tree to assign the class label by majority vote. So basically, if we've got 10 trees, we take 5 of them say that it's one, and then 3 of them say it's another, and 2 say it's another of the classes. Then we're going to go with the majority vote, is what we'll do in this particular case. So I did an example here where I did a random forest of 10 trees on my data. Remember that my data was a tiny amount of data, so this is a bit iffy. You can see that it's what it ended up with here, and you can see that we've ended up with a section there that did not appear in the previous one, and that's probably happened because of the fact that there's nothing green beyond this point. So in some of them, it clearly would have worked out in a situation where it would have made sense to divide them that way. So this is a random forest with 10 decision trees. If I use Gini, I got a Gini training score of 0.9722 and a validation score of 0.9375. If I use Entropy, you can see I've got the exact same training scores and validation scores. Again, don't be too surprised at this. Of course, the point is I'm using so little data here that it would be surprising if these things didn't almost come out the same. But the important point is that even though Entropy and Gini threw up different scores, as we said, they optimize very similar. You can look at this carefully to see if you can spot any differences. I did spot 1 or 2 differences. I think that is different from that. So obviously at some point it hit at some point. I think there are a few others. I think that's different than that, and so on. So there are minor differences between the models, presumably just because of the particular ones that were chosen. Now these are two important terms, bias and variance, and you'll hear this term bias now used a lot as well in terms of the ethical standpoint of machine learning techniques, where oftentimes bias from the outside world will seep into our models simply because it is seeped into our data. So something we do in the way that we've developed our model because of who we are, or something to do with the data because of where we've taken it from, will introduce a bias. But here we're using it in a much more general sense, where it's biased towards a particular set of data simply because it's seen more of that data. So there are a few different things, and oftentimes, and then of course variance, by the way, obviously is just how varied the answer can be, normally determined by variance, or the square root of variance, which is standard deviation. Now the problem is that when you try to optimize, let's say, variance, you often end up with a bit more bias, and if you try to optimize bias, you often end up with a bit more variance. So it doesn't always work out that way, but that can often be the case. So k is the number of trees in the forest, and it is a hyperparameter. So why don't we just use 100 trees or 1,000 trees, obviously, if we can choose as many as we want. So the larger the value of k, the better performance of the classifier, as it reduces the variance of the forest. but the worse the performance of the computation is of the computation, right? So if we use more trees in our random forest, we're going to have more computation in order to get our majority vote. If a decrease in the variance of the forest usually leads to an increase in the bias. And so you can see here that the situation would be that if we reduce our variance, we become more biased because we're more biased to the data that's there rather than anything else. But however, it's normally a decrease in the variance increases the bias, but by a smaller amount than you've got a decrease in the variance. So they can be useful up to a point. N and D, which are the number of samples that you draw for your bootstrap, remember width replacement, and D, the number of dimensions or features that you take at each point when you're making your decision. Those are both hyperparameters as well. If we decrease the size of decrease the size of n, in other words, if we take fewer samples each time, then we'll get significant variance in the results of the individual trees. You can see that back here, that if I only take, let's say, 5 samples in each case, then the sort of tree that I'm going to develop is going to be quite different in each case, depending on which samples that I've managed to randomly grab. So if I decrease the n, if we decrease the size of n, we will get significant variance in the results because each tree will be somewhat different in the individual trees, so the overall variance will increase. If I go for a large n though, this does the opposite, and this can lead to overfitting of the forest where every tree is coming up with the same thing because I've used nearly all of the samples. So it gives you less variance, but it's overfit, or it's biased towards that particular type of data, so it's an increase in bias. What they do in scikit-learn is n is usually set to the size of the training set. So just to be aware of this, what we mean by that. So my training set last time was 32, and we would set n equal to 32. But to be aware, remember with replacement, what's going to happen is that as we choose our 32 numbers, only some of the original 32 will actually be chosen, and a few of them will never get chosen, or will not get chosen on each occasion. So in other words, we might have 25 of them that are unique, and some of that 25 are chosen more than once. So that's what scikit-learn do. They set it to the size of the data set, knowing that some of them won't be some of them will be different on each occasion. They find that's a good trade-off. And okay, so we're up and going again there. So I think I'll maybe just start on that slide again. So for hyperparameter tuning, we said on the previous page that scikit-learn sets the value of n to be the size of the data set, and obviously, as we said, because of that idea of replacement, we're not going to get them all on each occasion. For the value d, what we do is we set it to the square root of the total number of features. So we take the square root of them each time. So as I say, if we have 20 features, we're going to take either 4 or 5, which is 4 point something is the square root of 20. That we'd maybe take 4 or 5 features on each occasion and make a decision based on those. If you want to choose the best hyperparameters for your data, if you want to go a little bit beyond what scikit-learn does as a default, you can try the following. In each case where a random tree is generated, there will be some of the training samples not chosen as part of the bootstrap set, and we showed that earlier. So there'll be ones that'll be not chosen there. Okay. Now I went a bit overboard here with not choosing them just to prove the point, right? So the 5 wasn't chosen, 3, 2, and 1, and so on. So there'll be some of them not chosen. It'll be far fewer than what I've shown there. It'd be more likely maybe a third of them won't get chosen. And these are called out-of-bag samples. Now it'll be a different third on each occasion because each time you randomly choose, and it'll be a different third or so that'll be left out. So for each random tree, you can use this set to see how well the tree generalized. So the ones you didn't choose, you can try those on the individual tree out of the random forest and see how well it generalized. And then you can use voting to see how well the forest generalizes overall. And you can then change the settings and you can start again. So this is if you're trying to see how well the different n and d values work, because obviously as you change n, you're going to have a different amount left out, and as you choose D, you're going to have a different amount left out. So you're going to get different results, is what I'm saying, and you can use that third that you've left out in order to kind of test the generalization of that. Okay, and you can start again. Now the thing is, this is a bit different from how we generalized the other ones, where we used a train and a validation set, and obviously a held out test set as well. So previously we had to separate we had a separate validation set for this, for what I've just said there. So can we just incorporate the validation set into the training set now? So in other words, can we just add these two together, because that held out that out of bag set is going to do that job? So the answer is kind of yes, but kind of no. So remember that the out of bag samples size changes with the hyperparameters. So depending on what value you pick for n, and remember it's those values that you're trying to pick, they change how big the out of bag size is, and therefore they change the effect of the validation size. So secondly, when comparing random forests with other model types, you prefer to be able to have the same validation set, or the same size validation set, in order to be able to test them. When comparing random forests with other model types, you would not exactly be comparing like with like, so it could give you a false sense of the generalization that's going on. In general, using a validation set is still the better method of hyperparameter tuning, but we do see that random forests are a little different from the other models in this regard. Okay, so I'm going to leave it at that for tonight, guys. Thanks for your attention. Until then.